Okay, welcome all. I'm going to discuss today absorption. Okay, so this is say is continuation of chapter 29, where you learned interface mass transfer. So this is basically application of interface mass transfer, like from liquid to gas or gas to liquid. So if you can remember, we had something like this. So y a is more than y a star the equilibrium. So mole fraction of gas is more than the equilibrium with the liquid, right? It means that mass transfer or driving force for the mass transfer will be ya minus ya star. So there will be transfer of mass from gas to liquid. So this is absorption. Liquid will absorb from the gas, right? And it is otherwise then liquid uh, mass transfer happens from liquid to gas. Okay, so this is absorption. So basically in absorption, what do you have? You have some component in gas. So gas is coming from it from bottom. Okay, gas coming from this. So in gas you have some impurity, ammonia, SO2, whatever. You want to get rid of that, okay, or you want to reduce the concentration of one component in the gas. Okay, so what you need a solvent which can take, so solvent coming from the top. Okay, solvent from top. L is the liquid, so which will absorb the gas, one component in the gas. So solvent coming from the top, okay, gas coming from the bottom and leaving from the top. Okay, so ya1 and g1 is the mass flow rate of the gas, okay, or molar flow rate of the gas. Okay, so ya1 and ya2. So ya1 is the will be more component, more fraction of one component, and then ya2 will be less because it is absorbed by the liquid. Okay, then you have solvent. Solvent may have some impurities a, or it could be from free. So I said xa2 could be 0. Okay, so solvent coming from the top and leaving from the down. So xa1, now it will absorb some a, the component a from the gas. Okay, so this is now let's see. G1 is the mole flow rate of gas. L1 is the mole flow rate of the liquid. Ya1 is the mole fraction of A in G1. Okay, and then ya2 will be G2 xa1 in liquid. Now you can see that what happens. This at each stage we will have liquid gas interaction, right? So there will be mass transfer from gas to liquid. So at each stage, composition is changing, right? And hence, this transfer is taking place. So even the liquid flow rate and gas flow rate, they are not constant. They are varying at each stage. Okay, that's why it is preferred to express these properties, mass fraction, mole fraction, L and A, these in terms of solute free, because solute concentration is changing from one stage to another stage. So suppose ammonia, so ammonia will get absorbed in liquid. So at each stage the flow rate and the concentration are changing. So what we do, we express in terms of solute free Ya, capital Ya is the mole fraction in terms of solute free mole fraction. So with whatever Ya is there, you subtract this. So capital Ya is Ya 1 over Ya. Okay. Similarly, Xa, capital Xa is solute free Xa over 1 minus Xa. So now for we will need also now LS and GS. Both are, so GS is basically G1 1 minus Y1, okay, or YA1, okay. So YA1 is mole fraction here. G1 subtract mole fraction of A. So GS is constant now, okay. And similarly, LS solid free flow rate will be L1 1 minus X1, okay. And similarly, it will be L2 1 minus X2, or GS will be G2 1 minus Y2 or YA2, whatever, okay. This also XA1 and XA2, XA2, XA1. So now hope you understand why we use LS and GS. Solute free flow rate, okay. This is what I was telling you. Okay, so now these how we can find. So in typical absorption column, what known, what we need to find, right? So feed, our feed is gas in, right? What gas in? In gas in, we know the concentration, right? We will know the flow rate coming in. We know that how much is the mole fraction of the impurity A. So this will be known. Okay. Now the liquid flow rate, how much is coming? Yeah, most likely it should be known. And liquid, the solvent which has how much A, or it is free, whatever, XA2 could be 0 or whatever the solvent we are using for the separation, right? Okay. And then so we need to find using the mole balance. We can find if 2 3 of them is given, the fourth one we can find. So how we can find? By applying mole balance. Okay, so G1 G2 L1. So now you can see L1 L2 G1 G2 if we use mole fraction, normal mole fraction. Okay, what we can do, we can use a solute free mole fraction LSGS. LSGS. Then there is no need for L1 L2 G1 G2. We can use only one of them. So our all mole fraction. So this is now see uh, A coming from gas, from liquid. This is gas. Mole of A coming through gas. Mole of A coming through liquid. This is both in. Then this is leaving. This is leaving. So Ya2 is leaving. XA1 is leaving. So we apply the mole balance. So this is important equation you need to understand. So if we combine GS, Ya1 minus Ya2, XA1 minus XA2, LS. So now see, we have only LS and GS. We don't have L1, L2, G1, G2. So this is the benefit of using solute free molar flow rates, LS and GS. Now, so this is the equation which will be our operating line for separation. So what does it mean? LS over GS is this. So what we know? We know YA1. We know YA1, right? XA2 in solvent we know. Then how it will change? So if we know LS over GS, so basically if you rearrange this, so YA1 we know. So how YA2, the YA2, how it will be? So it will be like this. Ya2, I'm just rearranging this equation. So it will be LS over GS times XA1 minus XA2 plus Y. Uh, uh, this. Okay, so y82, this is ya1 minus ya2. So ya2 will be this minus ya1. Okay, so basically, okay, so now see, this is slope. Y equal mx minus mx plus c. This is the slope. This is the slope of the operating line. Okay, so using this equation we can find one of them. If it is xa1, xa2, xa2 is known, we can find xa1. Okay, ya1 and ya2 will be known because we want to know how much we want absorption. So suppose ya1 is inlet, so impurity is 0.01, we want to reduce it to ya2 equal 0.02. So this should be known. Xa2 is the concentration of A in solvent. So we will know. So most likely we need to find this one. So we can find LSGS is known. Okay. So now we can see this will be our operating line. X1, Y2 is less. So X1, Y1. Okay, X1, Y1. We can find Y1 we know. We can find X1 using this. As I told you, X1. X1 from here. And then we can plot find this point x1 y1 here and x2 y2 here. So then you connect it, that's become your operating line. Okay, and equilibrium line is given, data is given, you can plot it. So now we can see uh, at y2 this is x2 and then this is equilibrium line, right? From here that's x2 star and x2 is this. So x2 star is more than x2. So x star is more than x. So what do we have? Liquid concentration is less than liquid concentration less than equilibrium one. It means that liquid can take from gas. Liquid take more. So that is absorption. Okay. Okay. Now okay, this one we said okay. Now finding the minimum this ls over gs minimum. Okay, ls over gs minimum, how we can find? Now see, what is the minimum flow rate you need? As a chemical engineer, you are like, when you are designing this absorption column, you need to set the flow rate of the solvent. How much flow rate you need to achieve some separation, right? So what value you should use? I mean, you don't know. Uh, so first of all, try to find the minimum flow rate. Minimum flow rate means that minimum flow rate of solvent which will make the separation possible. Okay, the ideal scenario. What will be the ideal scenario? In the middle, yani we cannot predict much. What we can predict? We can predict the leaving stream of the solvent. So leaving extreme, leaving, this is leaving from the column. So XA1, what will happen if we use minimum flow rate of solvent? And then what happens? This XA1 will be in equilibrium with YA1. Okay, so we want more, but the minimum flow rate will give me the concentration of XA1 will be in equilibrium with the YA1. Then only separation is possible. So minimum, this is the, so XA1 will be the XA star depending with respect to the YA1. Okay, is this clear? So as we increase the flow rate, separation will be possible when the minimum condition is these, yani XA1 and YA1, they are in equilibrium. So then we will use a factor. So this is ideal scenario. Separation is not desired, I mean not very good, but that will make, yani we need to use more than this. So LS over GS, minimum, LS minimum will be corresponding to a value of XA1 which is in equilibrium with YA1. Okay. So what is that? So minimum will be is this. So for example, if you have this is the equilibrium line, this is the equilibrium line, okay, and then your y2 is this, suppose this is y2, so and equilibrium, this is equilibrium with y2, this is x, so your operating line, this is will be like this. So that's the LS minimum. So this is the slope, LS over GS, right? Slope GS we know. So now for example we can do this one, this example. Now see, the equilibrium data is given. What inlet gas flow rate? So what is this? Inlet gas flow rate is given. So this is G1. Ammonia free water. Water is solvent. Okay, at this. So L2 is this. G1 is this. Okay. Ammonia free means X2 is 0. Right? Solvent, there is no ammonia. And now what else we have? We want to reduce the concentration of ammonia from 3.52 to 1.5 to volume percent. So volume fraction is same as mole fraction. So now what do we have? We have YA1, small YA1. Okay, this is not. So this is percentage. So this is 0.0352 and YA2 is 0.0129, right? So what we have to define the ratio of LS. So LS actual by LS minimum. Okay, so this is the actual LS actual we know, isn't it? It is given ammonia free water. This is L1. Okay, so from L1 we can find, so GS we can find, right? GS will be G1 1 minus YA1, right? LS will be L1 1 minus X, sorry, L2 1 minus X2, right? So X2 is 0, so LS will be same as L2, and GS solute free gas flow rate we can find. Okay, So minimum again. Okay, so let's see. This is so this is what I already explained. This is G1, L2, X2 is 0, Y1 and Y2 is this. So now the G1 is in which unit? G1 is monometric flow rate. G1 is volumetric flow rate. So this is like volume. So using the gas law, we can find the molar flow rate. So N is mole, but it could be molar flow rate N dot, which is PV over RT. So V is molecular flow rate, V dot. Okay, so that gives you this one. So per unit area is constant, so we can just say so this. Now GS1 minus Y1. Okay, L2 is same as L2 is this. Okay, yeah, okay, gram per second change to mole. Okay, divided by the molecular weight. L2 1 minus X2. X2 is 0 because solvent is independent of is free from the component, free from the solute. There is no solute there, right? So LS over GS is this. Now the minimum, how we can find the minimum? So you can see LS over GS is basically what we have. LS over GS is this, right? YA1 minus YA2. So Y capital YM or YA1 minus YA2 divided by XA1 minus XA2, right? YA1 in gas mole fraction of A in out. This is in XA2 0. XA1, this is for minimum LS minimum. What I said, XA1 is basically XA1 star for the minimum flow rate. So XA1 star with respect to the YA1, as simple as that. YA1. So if we have data or we have equation, whatever, so whatever the YA1 is there, YA1 is there. If we have any equation, M XA1, sorry, okay, okay, so this is also, you can put it like this. So YA1 or equilibrium data is not solute free, so basically we have YA equals, suppose if we have something like this, so YA1 XA1, so YA1 is known always. If we have equation, linear equation, then we can get XA1 star or from the data. Okay, so YA1 is known, isn't it? YA1 is 0.0352. So using the data 0.0352, so Y, so what, where are we? 0.3, so right, so point, this is 0.3, so it's something like this. Then we read this. Okay, so around 0.03. So it will be around 0.03 299. So this is X1 or XA1 star. Okay, so in this case, yeah, this is what equilibrium. So you put this X star, that's LS over GS. Okay, so minimum flow rate, you get it by this, and then you can design, like for example, in this case it is, so ratio will be 1.38. So you get the minimum, then as chemical engineer you design it to like 1.5 times, 1.4 times the minimum, so LS. Okay, so minimum ratio of this is 1.38. Okay, so this is fine. Okay, so now the next part is this is for stripping. Okay, so this is everything will be in different uh, just opposite of this. One thing is to find the length of using this equation. Okay, find the height of the tower. Okay, so I will post the second video. This is 25 minutes already, by today, tonight or tomorrow morning. Okay, I will stop here. Just we've covered now the basics of absorption, and this one is easy, but I will explain to you how to do this integration and find the z and so on. So please wait for my next video.